Well, this is John Black, Super Chemist. This is part 6. We got cut off on the last video, but I want you to understand this cosine and sine squared. When you have equations, sometimes it'll be squared, right? And sometimes it's not squared. When it's squared, like in the this kind of thing here, where you're doing the intensity thing, yeah, it's squared. So the cosine part of it is the percentage. You have to times it by 100, but it's the percentage of the good stuff. The sine is the percentage of the bad stuff. But when you have, like this thing with force, right? You don't square the cosine theta or the sine theta. When it comes to that, all they're doing is breaking down the forces into the x-axis and the y-axis. So it's not really a percentage. Like this here, if you had the force of 5 newtons, they break it down to the x and the y-axis. But you can see, right, because I did a 3, 4, 5 triangle there, right? When I add them up, though, 4 plus 3 does not equal 5, man. They're not equal in any way, okay? You know what I mean? You can see when you square it, right? 4 squared and 3 squared, you know what I mean? And figure this out. See, it's 5, and looks up here, it's the same up there at 5. So if you square it, you know what I mean? See right here? These two, they add up to, or squared, they equal 1 times 100, which would be 100%. Cosine theta plus sine theta, when you're not squaring it, it's not a percentage. Anyways, let's move on to the next thing. An analyzer does not move, but the photon rotates. So the analyzer is the cosine theta, or proportional to it, right? The analyzer is always proportional to cosine theta. So it must form a right angle with sine theta, okay? And the last thing here, the analyzer cannot be both the cosine theta and the hypotenuse. No one can be both things. Now this is the last thing about this. There's no math or anything. But I want you to look at these two pictures, right? And look, after you know where the analyzer's at. You're given that. You're told the orientation of the photon, right? All you have left is, and obviously the angle between these two lines is going to be the theta, right? Now all we need to do is put our sine on there, right? Now we can either put it on like this, or we can put it on like this. This is wrong. This is right. And why is that? Because, look, remember our rule. Cosine theta, right, has to include the right angle and the theta, right? Look over here. We know that the analyzer, in all of these cases, the analyzer is always the cosine theta. You can see over here, up and down, cosine theta. So you have two choices, because one of these is going to be rotating around, right? It's not going to be the cosine theta, because we already said cosine thetas cannot move out of their axis, right? Yeah, you can move the filter, but do you do that during an experiment? No, you keep it static, right? This way we have the angle and the theta on cosine theta, right? And then the hypotenuse, which is obviously, it can go around the thing because it's a hypotenuse. That means it's going to be a diagonal sometime. Over here, where it's wrong, the angle and the theta, they're not on cosine theta. And this line that you form, right, it goes from this circumference down to the other line, and it makes a right angle, just like over here. It starts at the circumference, goes down to the other line, and forms a right angle. Now, here, right, we know this is cosine theta, right? This is the new sign, right? Are they perpendicular? No. So they have to be perpendicular. Look over here. See how the orange line and the black line, they are perpendicular. So those are all those reasons why this is right, okay? What am I labeling them? I got these E naught and the cosines. We already discussed the cosine and sine, right? But why am I labeling these E naughts, okay? The reason why is, so we know the E field determines stuff, okay? We know that intensity, right, is proportional to E naught squared. and then that's how we got all this formula, right? I mean, this whole thing is based on the E field of the photon, right? I mean, we all know that, right? So obviously, I'm going to label that, for the E field, right? And this red line represents the photon. There's only two things involved here: a photon and an analyzer. There's only two things. So the analyzer is just static; it ain't doing nothing. So the photon, it's the one that has the oscillating field. The E field determines, stuff: who gets in, who don't, who passes the filter, who doesn't. So that's why I labeled that. Okay. Now, why did I label this over here? Because, cosine theta does not equal the x or the y axis, okay? Right here, it equals adjacent over hypotenuse. So if we take this equation and both sides we multiply by hypotenuse, right? Down here, see? Have the h up here, these two h's will cancel out and you'll be left with an a, which is adjacent. And then on this side you'll multiply by hypotenuse and you'll have cosine times hypotenuse. That's why I made this is that side, the adjacent side. And the same thing with the sine. We knew it was sine theta, right? But it'd be opposite over hypotenuse, right? We did multiply by both sides by hypotenuse. We'd end up with opposite here and h sine theta here. So that's what I put there. So what do these lines actually represent? The E field of the photon is the red line. The E field of the analyzer is the black line. Okay, and in my opinion, it's also the B field. All these types of diagrams like this, they represent a million things because so many things are proportional. Power, energy, force, they're all proportional. You know what I mean? Everything is proportional in some way. So yeah, but it's the E field and the B field of the photon, and this is the E and the B field of the analyzer. And I'm making up a word here, the probability curve, but this is basically the probability curve, man. It's we didn't even bring up the B field yet. Okay, we're still going to get to the B field. Okay, I've only heard one person ever bring up the B field except for me, and that was recently. Someone posted, so he actually sounds like a smart guy. Anyways, so shout out to that guy. But this is just you could say a voltage difference or a current difference, or B field difference, E field difference. What they'll get, half of the physicists are kind of right and half are wrong. Alright, but they will try to tell you that this is about amplitude. Okay, the amplitude of the actual photons. Okay, the photon's amplitude gets greater, this or that, whatever. No, first of all, a photon's amplitude is set by Planck's constant. Okay, it can't change. The only way you can change the energy is by changing the frequency, right? But intensity is different, right? Because it's not talking about energy. It's talking about energy per area, right? So it changes. When they're talking about intensity, right? They're not talking about, even though they say they'll describe it as a higher amplitude. Okay, the amplitude they're talking about is not about, half of them do because they're idiots, but the other half, they're not saying that. When they say they have a greater intensity, right, they're talking about more photons per second, right? The greater the number of photons per second, the greater the intensity, the greater the amplitude. But this is a mathematical, they turn up the intensity by making more waves, not by giving more energy to those waves they already made. Okay, amplitude is not the amplitude of the photon; it's the amplitude of the wave function, right? That represents a graph. That represents a superposition of a whole group of waves, not of photons, not just one. It always has to be a whole group, superposition, right? A superposition is a mathematical construct, a graph. It's not real, okay? I mean, if you're talking about waves, yes, so obviously it's real. but only to a point. You know what I mean? It's a representation. You know what I mean? Most times when they're talking about a superposition, it's just BS. It's just a mathematical construct. It doesn't even represent anything, really, because they're just lying about what it represents. This is what I'm talking about. See, here's a red photon, right? When they say they increase the intensity, right? They don't make this amplitude bigger. They create more photons. If it's radio, they create more photon radio waves. So here's their new intensity, right? When they make a superposition, right, of these two photons, they add them together and the amplitudes get greater. This is the superposition. It has a greater amplitude. But this superposition is a fake. It's a mathematical representation. It's a mathematical construct. It doesn't exist. It's a graph. So when they say this photon got a greater amplitude, they're talking about a graph, not a photon. Okay? So, yeah, the graph. Yeah, the superposition on a graph. Yeah, the amplitude gets bigger. But so what? I can draw a picture of anything. Doesn't make it true. Okay? I can draw a picture of the leprechauns. Does that mean leprechauns exist? No, they don't. Okay? But anyways, when the normal, or at least semi-normal physicists who say, you know, they're talking about photons, not maybe this case, but any case, and they're saying the amplitude of the photon gets higher, you know what I mean? Most times they're talking about a probability wave, right? A lot of times when we're talking about a photon having a greater amplitude, they're talking about the amplitude of a probability graph. The greater amplitude just means that the greater probability. Because the graph is in a wave, right? If it has a bigger amplitude, right, you have a more probability of whatever happening, you know. But most times, that's what they're talking about, okay? But the whole point is, when they're talking about the amplitude of a photon, you know, changing, being greater or smaller, they're never, ever, ever speaking about actual photons. They're either talking about the superposition, or they're talking about the wave function, probability wave. And to give you another example, what about AM radio? That's called amplitude modulation. Yeah, it means the radio modulates the amplitude of the voltage, not the actual photons. It modulates the amplitude of the voltage of a high frequency carrier wave, right? Amplitude is the power of the radio signal, and the power of the radio signal is dictated by the voltage applied to it, right? It has nothing to do when, you know, amplitude modulation has nothing to do with changing the photon into a bigger amplitude, because it's not possible, okay? And why is it not possible? The amplitude of a photon is constant, just like its velocity. Hence Planck's constant. Constant. The amplitude is constant. That Planck's constant. Get it? Yeah. What does this mean? We went over this in my Planck's units video, okay? What does this mean? 6.2626 times 10 to the negative 34th joule per cycle second. What does that mean? That means you take a second, like over here. Look, I got a second. There's a second. Here's a second. Here's a second. Right? And then I count the number of cycles. See, because you get this many joules per cycle, right? So this second on this photon, you can see it only has one wave, one cycle. That means it gets 1 H of joules right here. This is an H of joules, right? What about this second for this photon? Now he's got 2 cycles. So he gets 2 H of, you know, joules. And this is the H. H is this, right? Here's another second, right? This guy's blue though, right? He's got 1, 2, 3 cycles. So he gets 3 H of joules, right? And an H is, 1 H is this. This is how many joules, right? Now, if you believe that the photon can change its amplitude, okay, then what is this formula right here, down here is E equals HF. Yeah, the reason why this works is because H is constant, which means the amplitude is constant. You can only change the energy by changing the frequency on a photon. Water waves, okay, they travel at a constant